Hello everyone. In today's class of mine, I'm going to teach you about molecularity. But before I start with the topic called molecularity, let us recap what we have learned so far. We are doing the chapter called chemical kinetics, and in that, in our last class, we finished about order. First, we discussed about the definition of order, types of order of reaction, followed by the numerical problem of order of reaction. Even I taught you how to find the unit of rate constant. In today's class, we are going to learn about is molecularity. Okay. Do remember, students, in chemistry, particles means it may be ion, atom, or molecule. I repeat again, in chemistry, particles means it may be ion, atom, or molecule. And during the reaction, what happens, students, is the particle takes part in collision. So there might be a collision between the two atoms, two molecules, two ions, or the collision may be between atom and ion, or molecule and ion, like that. And that number of collision which occurs between the reactant particles gives you the value of molecularity. And do remember, molecularity is a theoretical value. So some example I have shown you here. Molecularity, it is the number of reactant particles, means ion, atom, or molecule, taking part in collision. Why they take part in collision? To bring the reaction. And do remember, molecularity is a theoretical value. If you remember, in my last class, I have said you order is an experimental value. And do remember now, molecularity is a theoretical value. Let us see some example how to determine molecularity, for which I have given you 4 examples, students, here. Okay, PCl5, on dissociation gives PCl3 and Cl2. Now see the coefficient of the reactant here. It is 1. Therefore, the molecularity is 1. And if the molecularity of a reaction is 1, we call it by the name unimolecular reaction. Unimolecular reaction means whose molecularity is 1. Now, in the second reaction, if you see, hydrogen and iodine is reacting to form hydrogen iodide. And if you see the coefficient of the reactant here, 1, here is also 1. So 1 plus 1 makes it 2. So the molecularity is 2. And if the molecularity comes 2, we call it bimolecular reaction, means those reactions whose molecularity is 2. Now in the third example, if you see here, sulfur dioxide reacts with oxygen to give you sulfur trioxide, students. Coefficient of sulfur dioxide is 2 and oxygen is 1 here. So 2 plus 1 makes it 3. So its molecularity is 3, means it is a trimolecular reaction. So students, do remember, if the molecularity is 1, we call unimolecular reaction. 2 means bimolecular reaction, 3 means trimolecular reaction. And we determine it by seeing the coefficient of the reactant. By adding the coefficient of the reactant, we get the value of molecularity. Now let us see the fourth example. 2 hydrogen ion is combining with half molecule of oxygen to give water. Now many will say its molecularity is 2.5, because 2 plus half is 2.5, but I have written here 3. So it's a trimolecular reaction. Let us see how. Actually, students, as I said, collision may occur between ion, atom, molecule, ions, like that. So if you see here, this 2 is the number of hydrogen ion, and this 2 and this 2 will get cancelled. So as these 2 get cancelled, it means 1 atom of oxygen. So 2 hydrogen ion is combining with 1 atom of oxygen. So 2 plus 1 makes it 3. So it's not half, this 2 and 2 will get cancelled. So 1 atom of oxygen combines with 2 hydrogen ion, whereby the molecularity becomes 3, and it is a trimolecular reaction, students. So do remember now that if the reaction molecularity is 1, it's called unimolecular reaction, 2 bimolecular reaction, 3 trimolecular reaction. And now you have to remember this note, students. Molecularity cannot be in fraction. 2 plus half is 2.5, but as I said, it's 3. Because this is 1 atom of oxygen plus 2 hydrogen ions, so 3. So molecularity cannot be in fraction, but order can be. So molecularity can never be in fraction, but order can be in fraction. So just now you saw 2 differences between order and molecularity. Order is an experimental value, whereas molecularity is a theoretical value. Order can be in fraction, but molecularity cannot be in fraction. Order can be 0, but molecularity cannot be 0. You can see there is no reaction where the molecularity will be 0. So this gives you the 3 difference between order and molecularity. Now you can see the difference here between order and molecularity. Order is an experimental value, I said in my last class, because we determine it with the tabular experimental data, whereas molecularity is a theoretical value. Order can be in fraction, but molecularity cannot be in fraction. Order can be 0, molecularity can never be 0. So this difference between has come 3-4 times in ISC students, so go through this difference between. You can add one more point for both, giving their definition. So here you can give the definition of order, here you can give the definition of molecularity, which gives you 4 points. So if this question comes in the exam for 2 marks, you have to write 4 points. Each difference carry half marks. But if it comes for 1 marks, you can give 2 points or at least 3 points. Okay? So this is all about difference between order and molecularity. If you want, you can take the screenshot of it and you can save it, okay, for reference. Now we go to the next topic called elementary reaction. These are those reactions we say, students, in which the value of order and molecularity will be same. The reaction in which the value of order and molecularity will come same, such reaction is known as elementary reaction, students. And the example of elementary reaction is SN1 and SN2 reaction. SN1 and SN2. Now let us see what is this SN1 and SN2 reaction. Okay? Now you can see here, SN1 full form is like this: unimolecular nucleophilic substitution reaction. Unimolecular nucleophilic substitution reaction. Unimolecular nucleophilic substitution reaction. And the word unimolecular means molecularity is 1. Okay? And for such reaction, order is also 1. And since the value of order and molecularity is same for SN1 reaction, therefore it is an elementary reaction, because elementary reactions are those reactions in which order and molecularity value will be same. So since in SN1 reaction, order and molecularity value is same, therefore it is a elementary reaction. Similarly, another example is SN2. Full form. 2 means bimolecular nucleophilic substitution reaction. So since the word is here is bimolecular, means molecularity is 2, and for such reaction order is also 2. Since again order and molecularity is same for SN2 reaction, therefore it is an elementary reaction. So students, do remember the example of elementary reaction is SN1 and SN2, because in both the cases order and molecularity is same. So you can see out here what I have written. SN1 reaction order is 1, molecularity is also 1. SN2 reaction order is 2, molecularity is also 2. Therefore, both are the example of elementary reaction because the value of order and molecularity is same. If you want, you can take the screenshot of it for further reference. And you can learn more detail about this in the chapter called organic chemistry. Okay, I have just introduced 2 reactions to you. It is very important for competitive exam, even for the board exam, this SN1 and SN2 reaction, for whom you have to learn the mechanism. Mechanism means a multiple step of a single reaction. So you learn more in detail about this in organic chemistry part. Now, important note for you all. For multi-step reaction, rate equation, order and molecularity is determined by the slowest step. Do remember, students, a single reaction has a lot of multi-steps, okay? And in that multi-step, some are slow steps, some are fast. Do remember these 3 terms, rate equation, order and molecularity is determined by the slowest step. And since the slowest step determines these all 3 things, therefore it is a rate determining step, we say. So in objective question, do remember if the question comes, which of the following is regarded as rate determining step, option may be the slowest step, the fast step, the intermediate step, none of this. So the answer will be the slowest step, which determines rate equation, order and molecularity. Therefore it is considered as rate determining step. Now look out here. For all slow step reaction, the value of order and molecularity will be same. So in multi-step reaction, whichever is the slowest step, for that order and molecularity will always be same. Therefore, all slow step reactions are regarded as elementary reaction, because elementary reactions are those reactions in which the value of order and molecularity will be same, and in all slow step reaction of multi-step reactions, okay, order and molecularity value will be same. Therefore, we consider them as elementary reaction. So do remember this again for the objective students. Slow step determines rate equation, order and molecularity. Therefore, it is regarded as rate determining step. And do remember for slow step, order and molecularity value will be always same. Therefore, it is regarded as elementary reaction. Now, let us see one example of it. Okay, if you see this reaction, students, okay, NO means nitric oxide, which is reacting with hydrogen to give you nitrogen and water. And this is a single step reaction. I repeat again, this is a single step reaction. The kinetics of this reaction is explained by the following steps. So 2 steps is given. Okay, for this single step, there are 2 steps, students. But for some reaction, there might be 3 step, 4 step, or 5 step like that. But right now, for this reaction, we have only 2 multi-steps. Okay, and this multi-step is regarded as mechanism of this particular reaction. When you explain the reaction in detail, that is called mechanism. So this reaction is been explained in detail by these 2 reaction students. Therefore, these are the multi-step of this reaction. But others may have 2 or 3 multi-step. But in this case, only 2 multi-steps you can see here. Now the question is saying you, what is the predicted rate law? State the order and molecularity of the reaction question is saying. Okay, and if you see, it will be mentioned in the question paper if this question comes. In the bracket of multi-steps, slow and fast will be written. Okay, slow and fast will be written, but slow step will be only 1. Fast step can be more than 1, but slow step will be only 1. Okay, so do remember, now these 2 is mentioned to you. Now we have to determine the rate law, order and molecularity. Now let us see how to find this. So if you see out here, students, this is the same reaction which I have copied here for you. And this is the multi-step of this particular reaction, in which one is written slow, one is written fast. I repeat again, slow will be only 1. If there is 4, 5 multi-step, rest all will be fast. Now you have to determine the rate law, order and molecularity, students. And from where we can determine all these 3, as I said you earlier, from the slow step. And this is our slow step now. And these 2 are the reactant of the slow step. So these 2 are the reactant of the slow step. So how to write down the rate equation? First you write R equal to K. This is rate of reaction, this is rate constant, into concentration of the reactants of the slow step. So slow step reactant is these 2. So here I am going to write is NO, one of the reactant. Coefficient you write in the power. Hydrogen is another reactant. Coefficient is 1, you write in the power. So this will give you the value of rate law for this multi-step. And from where I determine this? From the slow step. Now, to find the order, you need to add the power. So when you add the power of rate law, you get order. So order is 2 plus 1. So 2 plus 1 will give you 3. Now you need to determine molecularity. And molecularity is determined by the coefficient of the slow step. And if you see here, coefficient is 2. And here is 1. So when you add these 2, it becomes 3. So the molecularity will come 3. But don't get confused, students. I got order by adding the power of the rate law. But I got molecularity by adding the coefficient of the reactant of the slow step. And again here you can see order and molecularity is coming same. Therefore it is an elementary reaction because the order and molecularity value is coming same. Therefore it is an elementary reaction, students. So if you want, you can take the screenshot of this also. Okay. Now, do remember, student, like these examples are given many in your book. So you can practice this way. Clear? You can practice this way. Other, which is given in your book. Now we go to the next topic. Okay, this is one of the important topic for board exam again. And it is known by the name pseudo unimolecular reaction. I made it important for you all. Do remember, student, the word pseudo means false. False unimolecular reaction. Okay, means false unimolecular reaction. So before we go to its definition, students, let us take its example by which you will understand better. Okay, example of pseudo unimolecular reactions are 2. There are many, but I have mentioned 2 out here. One is inversion of cane sugar. The other one is hydrolysis of ethyl acetate. ETHYL, ethyl acetate. So the 2 examples of pseudo unimolecular reaction is inversion of cane sugar and hydrolysis of ethyl acetate. So with the help of these 2 examples, I am going to explain you what is pseudo unimolecular reaction. So let us go first with inversion of cane sugar. Okay, the formula of cane sugar is C12H22O11. It is also known by the name sucrose. And this has to be reacted with water, okay, which is taken in excess. So now when you react cane sugar, that is also known by the name sucrose, with excess of water, you get here is glucose and fructose. You get glucose and fructose. C6H12O6 is called glucose, C6H12O6 is called fructose. Now you may be surprised here. Formula is same, but the names are different. Reason is they are isomer. I repeat again, glucose and fructose are isomer. Their molecular formula is same, but their structural formula differs. Reason, glucose contains aldehyde group, fructose contains ketone group. So since glucose contains aldehyde group, it is referred as aldose. Fructose contains ketone group, so it is referred as ketose. And do remember their molecular formula is same, but in the structural formula of glucose there is aldehyde group. In the structural formula of fructose there is ketone group, so they differ in functional group. Therefore, they are regarded as functional isomers. And more in detail, you learn about this in the chapter called biomolecule in class 12 syllabus. Now, when you react sucrose with excess of water, you get glucose and fructose. So let us get the rate equation for this. R is equals to K, concentration of the reactant. And here the reactant is, one is your sucrose and one is your water. And the coefficient of both is 1, 1, so we put the power as 1, 1 for this. Now, in this reaction, since water is present in excess amount, therefore, we consider its concentration as constant. Since water is present in excess amount, we consider its concentration as what? Constant. Therefore, this rate will not depend upon water concentration. It will depend only upon the concentration of sucrose. It will depend only upon the concentration of what, students? Sucrose. Not in water, because water concentration is more, so it is considered as constant. Now, if you see the power out here is 1, therefore, the order of this reaction is 1. And molecularity, as I said you earlier, we determine through the coefficient. So, coefficient here is 1, here is also 1. So, 1 plus 1 makes it 2. So, do remember, for all pseudo unimolecular reaction, order will be 1 and molecularity will be 2. That means it is bimolecular. That's why it's false unimolecular. Pseudo means false unimolecular, because actually they all are bimolecular reaction, because molecularity will be 2. So do remember the definition of pseudo unimolecular reaction this way. Pseudo unimolecular reactions are those reactions in which one reactant is present in excess amount than the other reactant. The reactant which is present in excess amount, its concentration is considered as constant, and the rate will depend only upon that reactant which is present in less concentration. And for such reaction, order will be 1 and molecularity will be 2. Not unimolecular, but it's bimolecular. So our molecularity will be 2. I repeat the definition one more time for you all. Pseudo unimolecular reaction. These are those reactions in which one reactant is present in excess amount than the other reactant. The reactant which is present in excess amount, its concentration is considered as constant, and the rate will depend only upon that reactant which is present in less concentration. For such reaction, order will be 1 and molecularity will be 2. So students, if you want, you can take the screenshot of this, okay, so that you can make the notes. So definition is, these are those reactions in which one reactant is present in excess amount than the other reactant. The reactant which is present in excess amount, its concentration is considered as constant, and the rate of reaction will depend upon that reactant only which is present in less concentration. For such reaction, order will be 1 and molecularity will be 2. One example I have shown you here, that is inversion of cane sugar. Okay. Now we'll see another example of it, but before that I'm repeating inversion of cane sugar again. Okay. So you can take the screenshot of this for an example of pseudo unimolecular reaction. So sucrose and water is reacting to give you glucose and fructose. Water is present in excess amount, so this will be the rate equation in the beginning. But since the concentration of water will be taken as constant because it is present in excess amount, therefore the rate will depend only upon the reactant which is present in less concentration, and in this example is sucrose. And since the power is 1, so order will be 1, and since the coefficient is 2, so molecularity will be 2. Now another example you can see for pseudo unimolecular reaction is hydrolysis of ethyl acetate. Hydrolysis means to react with water. Hydrolysis means to react with water, and who is reacting with water? Ethyl acetate. And this is the formula of ethyl acetate. Actually, students, this much is called acetate. CH3COO is called acetate, And when you put ethyl, C2H5, it becomes ethyl acetate. So when ethyl acetate reacts with water, students, you get two compounds. One is called acetic acid, one is called ethanol. Ethanol is also known by the name ethyl alcohol. Okay, to show you this reaction, I'm going here for a while. Look out here. CH3COOH is called acetic acid. If you remove this H, becomes acetate. And if you put here ethyl, it becomes ethyl acetate. And this is reacting with whom? Water, which is taken in excess amount like before. So here we have to break water this way, HNOH, H2O. Now this portion goes with H, whereby you get CH3COOH. Okay? And this portion goes with OH, whereby you get C2H5OH. So this is called acetic acid, this is called ethyl alcohol. Hope so you have understood the reaction now. Let us go back. So this is all about hydrolysis of ethyl acetate reaction. Now, rate equation, R is equals to K, concentration of the product reactants. One is ethyl acetate, one is water. Coefficient of both is 1, so power will be 1 each for both. Again, in this reaction, water is present in excess amount, therefore its concentration is considered as constant, and our rate will depend only upon that reactant which is present in less concentration, which is ethyl acetate out here. And the order will be 1 as the power is 1, and molecularity will be 1 plus 1, that is 2. So do remember, for all pseudo unimolecular reaction, order will be 1 and molecularity will be 2. If you want, you can take the screenshot of this for the example. Okay, now we'll see one question. Okay, regarding order and molecularity is an objective question, students. Now let us see how to go with this. For a reaction 2A plus B gives C as the product, the rate equation is R is equals to K, A to the power X and B to the power Y. This is given by the quotient. I repeat this, your rate law is given by the quotient. Now you have to find these 5 things, okay, which I'm going to solve that side. Okay, the same reaction I have copied here now, students. Okay, 2A plus B gives you C. Rate equation is given by the quotient and you have to find these 5 things. First of all, the question is saying you to find the overall order. At the power, you get the overall order and it will be X plus Y. The overall order is X plus Y. Now the question is saying you to find molecularity. So here the coefficient is 1. So coefficient 2 plus 1 makes it 3. So molecularity will be 3. Now you have to find the order when B is axis. As I said you have to find the order when B is axis. So if B is axis, its concentration does not, rate does not depend upon its concentration because B is axis, so hide it. So the rate will depend only upon the concentration of A and the power of that is X, so here will be X. Similarly, order when A is axis. So you know when A is axis, so we have to hide A because the rate will not depend upon the concentration of A. So when you hide A, rate will depend only upon the concentration of B and the power is Y, so the order will be Y. Now, is it a pseudo unimolecular reaction? Question is saying. If you see here, students, molecularity is 3 because to be pseudo unimolecular reaction, molecularity should be 2. Therefore, no, it is not a pseudo molecular reaction. The answer will be no, it is not a pseudo unimolecular reaction because its order is 3. Sorry, molecularity is 3, so it is not a pseudo unimolecular reaction. Okay, if you want, students, you can take the screenshot of this again. So it will help you out to refer. Okay, students, now we will see the expression of rate constant for first order reaction. Okay, if the time permits, I'll show you for zero order also. Clear? Now we are going to see the expression of rate constant for first order reaction. So let us derive it. So here I'm going to derive the expression, derive an expression of rate constant K for first order reaction. So now I'm going to show you the derivation to find the expression of rate constant for first order reaction. So whenever you start the derivation, you start with supposition. Let A gives you product be a first order reaction. I am supposing, students, I am taking a very easy reaction to you. Let A gives you product be a first order reaction. So if you consider this as a first order reaction, therefore the rate law will be R is equals to K, concentration of the reactant, and the reactant here is only one, that is A. And since I have taken it as first order reaction, I have supposed it as first order reaction, so the power will be 1. Now, actually this is the rate of disappearance of A. Why? Because A is the only reactant here, which I taught you in my first class. Now, what is the expression of rate if it is solid or liquid? So we write change in concentration of A by change in time. We are finding the rate for A, so change in concentration of A by change in time. And since A is in the reactant, as the time passes, the concentration of A decreases, so we write here minus. It indicates that as time passes, concentration of A decreases, which is the reactant. And this side will be K into concentration of A. Power 1, no need to write. Now bring A in one side, so minus by A, this will come down, and this side will be K dt. I have cross multiply here. Okay? Now what we'll do is integrating both sides. I think you all have learned maths. Okay, in maths integration you have learned in 11 also. So integrating both sides. So when you do the integration both sides, students, constant should be taken outside the integral sign. So here the constant is minus, so I am taking out of the integral sign. Now the left one is your dA by A, and this is the symbol of integral. This side the constant is K, which you have to take it out of the integral sign again. Constant has to be taken out of the integral sign, so here will be dt. Now you need to apply the formula of integration. I think you have seen this formula. Integration of dx by x is equal to log x to the base e. So similarly, integration of dA by A will be log concentration of A, and base will be E. Minus is out, so we'll keep it here. Similarly here, students, K is K. Now integration of dx you have learned as x. So similarly then, integration of dt will be t. After you open the integral sign, we have to put one constant called c, which is called integration constant. Okay, and let this be equation 1. I repeat again, this is called integration constant. Now our job is to find the value of c. To find the value of c, you need to consider this way. Okay, suppose when time was not passed, that is when time was 0, let the concentration be A0, initial concentration of the reactant. But as the time passes and becomes T, let the concentration be A for the reactant. I repeat again, initial concentration when time was 0, let it be A0, and after time T, the concentration of reactant becomes A. Now look out here. When T becomes 0, A will become A0. When T becomes 0, A becomes A0. So I like to write here, when T becomes 0, concentration of A becomes equal to concentration of A0. Now let us substitute this in equation 1. Let us substitute this in equation 1. Okay. So minus log to the base E, I am replacing A concentration with A0 now, is equals to, now T is 0, put here 0, T is 0, so put here 0, 0 into K becomes 0, no need to write. Okay, then what will remain here is simply C. So this is be equation 2, let it be equation 2. Now you got the value of C. Now what we are going to do now is we are going to put the value of C in equation 1. Now putting 2 in 1, putting 2 in 1, putting 2 in 1. Let's see what we get now. Okay, putting 2 in 1. So equation 1 is minus log to the base E concentration of A is equals to KT. Now this C I am going to replace with its value. So C is substituted with this value. So this value is minus log to the base E A0. So this is how I replace the value of C. Clear? Now I'll extend this further. Okay, just now we got minus log to the base E concentration of A is equals to Kt minus log to the base E concentration of A0. Now students, we will convert base E to base 10, okay? So whenever you convert base E to base 10, log base E to base 10, we multiply with 2.303 is equals to Kt again. Here also whenever you want to convert base E to base 10, we need to multiply with 2.303. Okay, A naught. So I have replaced log base E with base 10. Okay, after this what we will do is, students, we will take out the minus sign common. So when you take the minus sign common, minus will become plus, minus will become plus, plus will become minus, and again minus will become plus. I repeat again, I have taken minus sign out. So when you do so, minus will become plus, plus will become minus, and minus will again become plus. Clear? Now here what we do is, we will divide everyone with 2.303 now. So when you divide everyone with 2.303, let us see what we get, students. So when you divide everyone with 2.303, so when you divide this with 2.303, what remains here is this much. And you are dividing with 2.303 here. And here also you are dividing with 2.303, means those two will get cancelled and only this much will be left behind. Okay? And do remember, students, this actually gives me the equation of straight line for first order reaction. I repeat again, this is the equation of straight line for first order reaction, and you know equation of straight line is equals to y is equals to mx plus c, in which this act as y, this act as m, and this t act as x, and this act as c. So y is equals to mx plus c gives you the equation of straight line, and with the help of this equation of straight line we can make the graph of first order reaction that I will show you later on. So let us derive further now. Okay, now what I'll do here is I'll take this one here and I'll bring this one this side. So let us see what we get then. So if minus will go this side, we get is Kt upon 2.303 is equals to log to the base 10 A naught is already this side. So when this will come this side, plus will become minus. So you get is log to the base 10 A. Okay. Now let us solve further. Kt upon 2.303 is equals to, now here you use the log property, log m minus log n. So log m minus log n means log to the base 10 m by n. I repeat the formula, log m in minus log n means log m by n. Now let us bring this up and t down, keeping k one side. So k is equals to 2.303 upon t. This will go up, this will come down. 2.303 by t, log to the base 10 a naught by a. And this gives me the equation of rate constant for first order reaction. Students, the question said us to find the expression of rate constant for first order reaction, and this is the answer. Okay? Derivation has hardly come in your board exam. Derivation has hardly come in your board exam. But still, students, you need to go with it so that it will help you. Okay? Mathematical power will increase by you, for you all. And this is usually used in numerical problem. So in board exam, numerical problem comes to find rate constant sometime to find time, sometime to find initial concentration, sometime to find the concentration after time t. So this formula we use to solve the numerical problem of first order reaction. So students, remember this formula, k is equals to 2.303 by t log 10 a0 by a, to solve the numerical problem of rate constant for first order reaction. Okay? And this expression you need to remember to make a graph of first order reaction. Okay, so you can take the screenshot of this all derivation whatever I have done, and you can compare with the notes if you have. Okay, otherwise you can make the notes from here. Okay, students. Now we'll see the graph of rate constant for first order reaction. So before I show you the graph, let us see the expression which we got earlier. Log to the base 10a is equals to minus kt upon 2.303 plus log to the base 10 a naught. And as I said you, this gives you the equation of a straight line. This is y, this is m, and m means slope, minus k by 2.303, and this t is your x value, and this is the value of c. So do remember the rate constant for first order reaction expression we got from here. And for objective, do remember for first order reaction, what is the value of slope? Minus k by 2.303. Abscissa value is t, that is time. Ordinate value is log 10a, and this is the value of y-intercept. So from this we can make the graph for first order reaction. So let us see the graph now. So this is your x-axis, this is your y-axis. Okay. Now in x-axis what we have? Time, t, and in y-axis what we have? Log to the base 10a. Along y-axis we have this. Now since the slope is negative, so we get descending slope. Okay, if the slope was positive, we could have got ascending slope, but since it is negative, so we'll get a descending slope. And look out here, student, this straight line is touching y-axis here. This will give you the value of y-intercept. Okay, and the value of y-intercept is log to the base 10 a naught. So what is the value of y-intercept for first order reaction? Log 10 a naught concentration. Ordinate log 10 concentration of A, abscissa is T, which is time. And now if I draw a line out here to make a right angle, this angle, let us be theta, and this will give you the value of slope, because M stands for slope, also known by the name gradient, and slope actually means tan theta. Okay, tan theta, and the value of slope you got is minus k by 2.303. If you remember, I have given you the unit of slope for Arrhenius equation. Now let us see what is the unit of slope for first order reaction. So if you see, students, 2.303 is the number, minus is constant. So whatever is the unit of k, that is the unit of slope for first order reaction, students. And I have already said you the unit of rate constant for first order reaction is time inverse in my previous classes. So the unit of slope will be also time inverse, that is second inverse, minute inverse, hour inverse, year inverse, like that. Okay, because this is the rate constant for first order reaction, and for first order reaction unit of rate constant is time inverse, so the slope unit will be also time inverse. So it can be second inverse, minute inverse, hour inverse, day inverse, year inverse, etc. So this is the slope which I made it for first order reaction. So you need to remember the earlier expression, students, for numerical problem of first order reaction, and you have to remember this expression for the slope of first order reaction. Now similarly, we'll see the expression of rate constant for zero order reaction. Okay, now we'll see derive an expression of rate constant for zero order reaction. So just like the way I did it for first order, you have to suppose let A gives you product be a zero order reaction. So since you have supposed this reaction as zero order, so therefore the rate law will be R is equals to K, concentration of reactant, and here is one reactant, that is A. And since you have taken it as zero order reaction, the power will be 0. And actually this R is the rate of disappearance of A, because reactant will disappear. And as I said you, the formula is change in concentration of A by change in time. And reactant concentration always decreases as time passes, so sign will be negative. And this side should be K, because anything to the power 0 is 1, no need to write. Now just take this one this side. So when you do so, you get is minus concentration of A is equals to K dt. Now again, like before, you will be doing integrating both sides. And if you integrate both sides, what you have to do is you have to take the constant outside the integral sign. So this minus is constant, so outside the integral sign. So left is d of concentration of A, and here the constant is K, take it out, and only dt will be under the integral sign. Now the formula for this is this one. Integration of dx is x. So similarly, integration of dA will become simply concentration of A. K is constant. If integration of dx is x, then integration of dt will be t. After you open the integral sign, you have to put a constant, let it be c, which is an integral constant, integration constant, and let this be equation 1. Now similarly, like before, we are going to find the value of c, and we place inside this equation. So to do so, again I am taking one case. When the time was 0, let the concentration was A0, and when the time became t, concentration became A. Okay? So now look out here. If the time is 0, A becomes A0. So when t is equals to 0, then again A becomes equal to A0. So substitute this in equation 1. So now look out here. Minus, I am replacing A with A0. Time is 0, so 0 into K is 0. No need to write. So what remains here is simply C. Let it be equation 2. Now you are going to put equation 2 in 1. So putting equation 2 in 1, let us see what we get, students, now. Minus A0, equals to KT, and the value of this C, that is integration constant, is how much here? Minus concentration of A0. Clear? So this is how we get the expression. Now again here you take the minus sign out. If you take the minus sign out, minus will become plus, plus will become minus, and minus will become plus. And students, again this gives us the equation of straight line y is equals to mx plus c for 0 order reaction, in which this act as ordinate, that is y, this act as slope, that is m, this act as your abscissa, that is t, and this act as your y-intercept, that is c. So from here we get the expression of straight line for 0 order reaction. Now let us find first of all the value of rate constant for 0 order. Okay, so I'll bring this one this side, I'll take this one that side. So therefore what you get here is, if this comes this side, negative becomes positive, so you get KT is equals to A0 minus A, because this will go that side. So therefore K becomes A0 minus A by T, and this will give me the equation of rate constant for 0 order reaction. Again you have to remember this formula, students, for numerical problem of rate equation. I repeat again, you need to remember this for the numerical problem of rate constant for 0 order reaction, and this for the graph. Okay, so if you want, you can take the screenshot of this, so that is going to help you to express the to solve the numerical problem of 0 order reaction with the help of this particular equation. Okay. Okay. Now with the help of the equation of straight line which we got earlier, now we are going to make a graph for 0 order reaction. So this is the expression which we got for the equation of straight line for 0 order reaction earlier, students. Expression you remember for the numerical problem. Now this expression you remember for the graph and for objective quotient. And here this act as y, this minus k act as slope, t act as abscissa, and this act as y-intercept. So with the help of this, now we are going to make a graph for 0 order reaction. So this is x-axis, this is your y-axis, students. Along x-axis what we have is time, and along y-axis what we have is concentration of A after time t. And since the slope is again negative, so we get descending slope here, and this is a straight line, and this straight line is touching somewhere here. This will give me the value of y-intercept, students. And the value of y-intercept for 0 order reaction is A0 concentration. Now if I draw a rectangle out here, let this angle be theta, which will give me the value of slope. Slope means tan theta m, okay, which also means gradient, and the value which we are getting out here is minus k. You can see from this expression minus k. Now let us find the unit of slope for 0 order reaction. So if you see here, whatever is the unit of rate constant for 0 order reaction, the same will be the unit of slope. And do remember the unit of rate constant for zero order reaction is mole liter inverse second inverse. So this is the unit of rate constant for zero order reaction, and the same will be the unit of slope. Reason, because it is equal to K. And whether, let us confirm whether this is the unit of rate constant or not. Now you can see the power of the liter is what? -1. Add 1. If the power of the liter is given, you have to add 1. So if you add 1, -1 plus 1 makes it 0. So it is correct. It is the your unit of rate constant for zero order reaction, and same will be the unit of slope. So do remember the 3 units of slopes which I have given you so far. The unit of slope for Arrhenius equation is Kelvin. The unit of slope for first order reaction is time inverse. You can write second inverse, minute inverse like that. And the unit of slope, okay, for zero order reaction is mole liter inverse second inverse. And the formula which I gave you just now to express the rate constant for first order reaction was K is equals to 2.303 upon T log to the base 10 A naught concentration by A concentration. This is for first order reaction, students. And for zero order, K is equals to, we got, there is A naught minus A by T. So with this formula, we calculate the rate constant of zero order reaction. With this formula, we calculate the rate constant of first order reaction, students. And you need to remember the slope unit for all whatever derivation we have done so far. So for Arrhenius equation, slope unit is Kelvin. For first order is second inverse, minute inverse, time inverse. And for zero order is this. And along with that, you need to remember the graph. Okay? So in today's class, students, I explain you about molecularity. After doing molecularity part, we did some difference between order and molecularity. Then I explain you what is multi-step reactions mean, what is elementary reaction means. We saw 1-2 questions of that. Then I explain you to find the expression of rate constant for zero order and first order, for which expression has to be remembered by you all, which is going to help you in numerical problem. Along with that, we saw the equation of straight line for both the orders. With the help of that, I taught you how to make the graph and to remember the unit of slope. So in next class, I am going to teach you about half-life period. So after we learn about half-life period, students, we are going to see the relationship between rate constant and half-life period for zero order as well as for first order. After that, we are going to do the numerical problems of half-life periods for both zero order and first order, and we wrap the chapter. Okay? Thank you very much for today. Be safe, stay home. Thank you.
Hi, welcome back to Economics Class 12 ISC 2021. The last class, I was discussing about the movement and shift of the demand curve. Here, we saw that movement of the demand curve takes place when there is a change in the price. Other factors will remain constant. So, when the price increased, the quantity demanded decreased. Other factors remaining constant, there was movement along the same demand curve. And then we had contraction, that is, here when the price increases, quantity demanded decreases, etc. Then we talked about shift. Shift means the whole demand curve is going to move. There is increase in demand and decrease in demand. In increase in demand, price remains constant. Other factors change. Other factors could be the income of the consumer has increased. If the income of the consumer increases, then the demand will increase. When the demand increases, the demand curve shifts upwards, rightwards. Then we have decrease in demand. Decrease in demand, price will remain constant. Other factors change. Example, income of the consumer decreases. Or let's have another case, price of the substitute goods. Now, in price of the substitute goods, if the price of the substitute good, let us say we are drinking tea, and the substitute good is coffee. So if the price of coffee, say decreases, that is the substitute good coffee, whose price decreases, what happens to the demand? Demand for a commodity will increase. So, if you want decrease in demand, you will have to make sure that the price of the substitute good has to fall. When the price of coffee falls, there is, what happens? There is increase in demand. So, if the price of the substitute good coffee increases, people will switch over to tea. People will start drinking tea because coffee, the substitute good, is costlier. So, when people start drinking tea, demand for tea increases. Here what happens? The whole demand curve shifts leftwards and downwards. That was on movement and shift of the demand curve. More question based on movement and shift of the demand curve. I will come back to it in the chapter Market Mechanism, which we will do later. Here we will have to brush up what we studied regarding movement and shift of the demand curve. Then I will do some graphs. Today I am going to start with elasticity of demand. Elasticity of demand means how much will the demand change when factors change. If the price changes, how much will the demand change? If your income changes, how much will your demand change? If the price of another commodity, substitute good or complementary good changes, how much will the demand change? The first one I am going to discuss is when there is a change in the price, how much will the demand change? It's called degree of responsiveness. Let us see the definition. It is the degree of responsiveness. Degree of responsiveness means how much will the quantity demanded change. Degree of responsiveness of quantity demanded of a commodity in response to the change in price. What does it mean? It means if there is a change in the price, how much will the quantity demanded change? Now, let's look at some goods like insulin for diabetic people. If the price of insulin shoots up, it's a double the price, or it increases by 50%, then what will happen to the quantity demanded for insulin? Will it decrease because the price has increased? No, there will be no change in the quantity demanded because insulin is necessary for diabetic people. Whereas if you see luxury goods like LED TV or luxury items, what happens is if there is a small change in the price, LED TV sale 5,000 rupees off, when there is a small fall in the price of LED TV or any luxury goods, there is a drastic increase in the quantity demanded. Means that luxury goods are very sensitive to price, whereas necessity goods like salt, like insulin for diabetic people are not sensitive to the price. So even if the price changes, quantity demanded won't change much. But if luxury goods item change a little bit, price changes a little bit, the demand will change drastically. So how much will the quantity demanded change when there is a change in the price? Here you will see there are 5 types. 1, 2, 3, 4, 5. Perfectly inelastic, inelastic, unitary, elastic, and perfectly elastic. So these are the 5 ways of how, when there is a change in the price, how much the quantity demanded will change. I will start with price elastic demand and I'll explain how these values come. After this, my next class, I will teach you income elasticity of demand. Income elasticity of demand will be my next class, and thereafter I'll teach you cross elasticity of demand. So there are price elasticity, income elasticity, and cross elastic demand for your ISC syllabus. Let me start with price elastic demand. Now you know the definition. Now I come to the first one, perfectly inelastic demand curve. Now I want you to watch the whiteboard and I'm going to explain here. The first one is called perfectly inelastic demand curve. Perfectly inelastic means Even if the price changes, there is no change in the quantity demanded. Let's have a look at a graph. This is your price, and this is your quantity demanded, as usual, x-axis, y-axis. This is your demand curve. Normally, it is downward sloping towards the right. But in perfectly inelastic, the demand curve will not be negative sloping, it will be straight. This is a perfectly inelastic demand curve. Here you will see that even if the price changes, increases or decreases, the price may increase, the price may decrease, but the quantity demanded will remain the same. To understand the valuation of EP is equal to 0, what is this then? To understand this, you have to know a formula. The formula is price elasticity of demand percentage formula. The formula is price elasticity of demand is equal to percentage change in quantity demanded upon percentage change in price. This is a formula known as percentage formula for price elasticity of demand. You have to know this to understand this. In the first case here, price changed, quantity demanded did not change. So, price change 0, no change in the quantity demanded. Price change, let's keep anything, say 10%, 20%, 30%, let's write 40%. Quantity demanded change, 0, no change. Price changed, yes, let's say 40%. 0 upon 40 is 0. So using this formula, we get EP is equal to 0. EP is equal to 0. 0 upon 40 is 0. So this is an example of perfectly inelastic demand curve. EP is equal to 0. An example would be, you can have, it's rare, but you can keep insulin. Insulin used by diabetic people, even if the price changes, the quantity demanded will not change. EP is equal to 0. So your demand curve is vertical or parallel to the y-axis. Parallel to the y-axis. This is the first one, perfectly inelastic demand curve. The second one is inelastic demand curve. Now, when I explain this, you will notice that the demand curve has to be negative sloping. So every time you have demand curve, it should not fall this side and become positive, it should fall this side and become negative. So there are steps of how to remember. If this is the demand curve, this is perfectly inelastic demand curve. Second one, make it fall like this. Third one, make it fall. Fourth one, make it fall more, and the fifth one will be parallel to the x-axis. Let's do the second one. In the second one, that is inelastic demand curve, the demand curve will fall slightly like this. So we have steep demand curve. This is your price, this is your quantity demanded. Let's see. Change in the price, so much. It could increase, it could decrease. This is the change in the price. And what happens to the quantity demanded? There is a very small change in the quantity demanded. Price changed a lot, but the quantity demanded changed very less. An example would be EP is equal to, let us say, percentage change in the quantity demand. Very small change in the quantity demanded, 10%. And the change in the price is more, say 40%. 10 upon 40. 10 upon 40 is 1 upon 4, 0.25. So we say EP is less than 1. EP, like we had EP is equal to 0, now EP is less than 1. Less than 1, EP means delta P is greater than delta Q. You have to write, very important, delta P is greater than delta Q. You have to write this when you draw this diagram. Delta P is greater than delta Q. An typical example of inelastic demand curve is necessity goods like salt. You could have other necessity goods. I am giving you one simple example, salt. Salt is a necessity good. Even if the price changes by 40%, the quantity demanded will change by just 10%. Delta P is greater than delta Q. That is the second one. Now the third one is unitary. Make sure now we will make the demand curve fall more. EP is 0, EP less than 1. Now we are going to have EP equal to 1. 0, less than 1, 1. So let's have a look. So we are coming to the third one. Unitary demand curve. Unitary means equal to 1. In this, we make the demand curve fall more. This is your price. This is your quantity demanded. Change in the price, delta P. Change in the quantity, delta Q. You'll notice that change in the price and change in the quantity demanded is equal. Delta P is equal to delta Q. Important to write this. Let's see. EP is equal to percentage change in the quantity demanded upon percentage change in the price. Let us say the price increased by 50%, which led to fall in the quantity demanded by 50%. EP is equal to 1. Unitary. This is unitary demand curve. EP is equal to 1. Let's go back. EP is equal to 0. EP is less than 1. EP equal to 1. EP is equal to 0. EP is equal to less than 1. EP is equal to 1. An example of this is normal goods. Anything. A TV, a fridge, a car, a house. All normal goods are example of this. Here, delta P is equal to delta Q. When you calculate, change in the price and change in the quantity demanded will be same. That's why EP is equal to 1. Unitary. In this, you have to notice one more thing I want to explain is the word rectangular hyperbola. Now what is this rectangular hyper? Very simple. It just means that when EP is equal to 1, when EP is equal to 1 unitary, the demand curve is a rectangular hyperbola. Simply means that if you were to take the demand curve, where delta P is equal to delta Q, let me take a point here and find the area. If I find the area of this, area of a rectangle, length into breadth, and I take another point anywhere here, and I find the area of this also, you will find area of the blue portion and area of this black portion, the area will be same. That means demand curve is a rectangular hyperbola, means any point on the demand curve, below that whatever area you get will be equal. So you take this point, area, you take this point, find area, it will be same. This is called rectangular hyperbola. Very simple. The next one. After this, we make the demand curve fall more, and we get elastic demand curve. So the fourth one. Now we make the demand curve fall more inclined. This is the price, this is the quantity demanded, origin, x-axis, y-axis. Notice the change in the price, very small change in the price. Notice the quantity demanded, huge change in the price. Delta Q is greater than delta P. Which means a small change in the price will lead to huge change in the quantity demanded. EP is greater than 1. How does this come? EP is greater than 1. Again the formula, EP is equal to percentage change in the quantity demanded. Let us say this is 80%. Quantity demanded changes 80% and change in the price is say 20%. If you want to give an example, let us say the price of LED TV falls by 20%. When the price of LED TV falls by 20%, then the demand, the quantity demanded for LED will increase by 80%. 80 upon 20, you will see it is 4. EP is greater than 1. Again, let's go back. EP is equal to 0. EP is less than 1. EP is equal to 1. EP is greater than 1. This is elastic. Very sensitive to the price, elastic demand curve. EP is greater than 1. Delta Q is greater than delta P. A typical example, any luxury good. Luxury good like, I say, LED TV, SUVs, high-end mobile phones, iPhones, OnePlus 8, all these luxury items, a small change in the price leads to huge change in the quantity demanded. The next one, the fifth one, is known as perfectly elastic demand curve. Perfectly elastic demand curve, the fifth one. So, here the demand curve is parallel to the x-axis. Parallel to the x-axis. Price, quantity demanded. So the price will remain same, but the quantity demanded could be any amount. Q1, Q2, change in the quantity demanded could be any amount. No change in the price. So if you were to use the formula, EP is equal to percentage change in the quantity demanded upon percentage change in the price. Let us say the percentage change in the quantity demanded is 60%. And percentage change in the price has not changed, 0%, is equal to infinity. So EP is equal to infinity. This is perfectly elastic. Perfectly elastic, a very rare case. So example won't be there, but this behavior of the demand curve, which is parallel to the x-axis, actually takes place in a perfect competition, a perfectly competitive market, which you will learn later when we explain the different forms of market. In that, you will understand that at this price, buyers will demand any amount. Because in a perfectly competitive market, everyone knows the price, and the price is same for all homogeneous good. So when the price is same anywhere you buy, the price is same, so quantity demand can be. But any price above this, if the price increases, since the consumers who are buying and demanding knows the price, nobody will buy it. Then you might think, what about if the price falls? Now, in the chapter Forms of Market, you will learn that if the price falls, then the firms will face loss because they just make normal profit, and when they decrease the price, they'll face loss. And nobody wants to sell when they are making loss, and some of the companies will leave, and there's other things that you have to understand in Forms of Market. So the price will not fall. At this price, all will buy, or Anything above this price, nobody will buy. Perfectly elastic, that takes place in a perfectly competitive market. So, what did we learn? We learned the 5 types of price elastic demand. How to learn? In short, EP is equal to 0. Insulin, make it fall slightly. EP is equal to less than 1. Example, necessary good, salt. Make it fall more. Unity, EP is equal to 1. Unity, normal goods. Make it fall more. EP is greater than 1. Elastic. Example, luxury goods, LED TV. Fifth one, EP is equal to infinity. Example, perfectly competitive market where at this price, consumers will buy as much as they want, whereas higher than that price, nobody will buy. Okay? So this is price elasticity of demand. In short, sometimes you will be asked, draw graph showing perfectly inelastic demand curve, or draw a diagram to show elastic demand curve with an example. The next thing I'm going to teach you in my next class, which I'm going to give you a gist of what I'm going to teach so that some of you would like to see the textbook, read it beforehand and understand. The next topic, let me explain in short for the next class. I'm going to teach you, the next thing is called income elasticity of demand. Income written like this. This is sign of income. Income elasticity of demand. We write E with a Y. And you will understand that the income elasticity of demand is again percentage change in the quantity demanded upon percentage change in not price but income. So when your income changes, how much will your quantity demanded change? How much is the demand sensitive to the change in price? In this, we'll understand that there are 3 parts. We have negative income elastic demand, positive, and 0. So anyway, this is what I'm going to teach you in the next class, income elasticity of demand, where this is your formula. Then I'm going to teach you cross. Cross means two different goods. Cross takes place when there are 2 goods that we are talking about. Income and quantity demanded is different. Price of one commodity and its demand is different. But cross means price of one good and the demand for the other. So in cross you will understand there are either the good is related or not related. If a good is related, substitute good. If a good is related, complementary good. Or the good is not related. So in my next class, I'm going to discuss income elastic demand. This is your formula. What are the 3 parts? Then in the next class, I'm going to teach you cross elasticity of demand, where cross means price of one good and demand for another good. So how can it be related? It could be tea and coffee, substitute goods. It can be complementary goods, that is petrol car and petrol, or not related, TV and chair, no relation. So this is what I'm going to teach you in the next class. So this is all for today. And in my next class, I'm going to start with income elastic demand and cross elasticity of demand. Thank you so much. Hope to see you in the next episode. Thank you.
Welcome back, children. We will continue with our literature in English classes online. And today we are going to move on to the next poem in our syllabus, the 8th in this series, John Brown. Now, before I begin with the poem, certain things again you will have to keep in mind. First of all, when you look at the title of the poem, John Brown, obviously it's the name of a character, the central character in the poem, who was a soldier, who went to fight in a war and returned home wounded, injured, maimed, disfigured. And through this character and through the character of the mother of John Brown, the poet Bob Dylan is bringing out the anti-war theme in this poem. Now, before understanding the anti-war theme in the poem, we will have to understand what was the traditional or the conventional attitude towards wars. Now, when you look at history and when you look at literature in various parts of the world, you will see that from the ancient times in literature, in various languages, be it Roman, be it Greek, be it French, be it Latin, be it English, wars have been glorified. Soldiers have been glorified. The profession of a soldier was considered to be the best profession, the yardstick to measure how patriotic you are. Most importantly, this glorification of wars, this glorification of soldiers, this glorification of martyrdom in the battlefields, obviously in literature pointed to the fact that wars were something to be proud about. It was something glorious. It was a place of showing your courage, bravery, heroism, patriotism. And if you died in the battlefield, there was nothing greater or more nobler than death in the battlefield. This poem is aiming to prick the bubble of that traditional, conventional belief that wars are glorious, wars are welcome, that soldiers play a huge role in the society, that the profession of a soldier is something to be anticipated, hoped, expected. It is like a dream come true in the life of a young man. This perception of the glorification of wars and soldiers, that is what the poet is aiming to prove totally wrong in this poem, John Brown. The anti-war concept, the theme, comes from this fact, and it comes through the character of the mother of John Brown, who in the beginning reacts to her son becoming a soldier in a particular way. She is happy, proud, joyful that her son has become a soldier. And we will see towards the end of the poem, we find that she realizes how wrong she was in her thoughts and conceptions about wars and soldiers. If you look at the poem and if you analyze what type of a poem is John Brown, this poem is a ballad. A ballad is a poem which tells us a story, maybe about heroism and courage, and at the same time, a ballad teaches us a moral lesson. This poem, John Brown, is in the form of a traditional ballad with 12 stanzas. Remember, this was basically a song written by Bob Dylan in 1962. The 1960s in America was the age of protests, rebellion, and therefore this poem, or songwriters like Bob Dylan, wanted to break the conventional beliefs and ideas by walking in the opposite direction of what people believed in. Until the 1960s, the American parents were very proud if their sons became soldiers. This was a result of the Cold War also, because during the Cold War, when the world was divided into two blocks, the American bloc known as the NATO and the communist bloc known as the Warsaw Pact, these two were having the Cold War. And during this time, the Americans believed that it was their moral responsibility to stop the spread of communism in this world. It was their moral duty to maintain peace and harmony all over the world. And therefore, America used to send soldiers and troops everywhere in all corners of the world in order to maintain world peace and at the same time to check the spread of communism. While doing so, the parents felt that they were contributing to this greatness of America by encouraging their sons to become soldiers. But when we read this poem, we find that the mother also had the initial belief which was similar to the other parents. The pride, the joy, the happiness, the glory that her son had become a soldier, and the final realization that battlefield is not a place where you go to win medals. Battlefield is a place of risks, dangers, where you can be wounded, injured, maimed, and even die. Another point I would like to tell you. Which year is this war in the poem taking place is not mentioned. Which war this soldier, John Brown, is going to fight, that is also not mentioned. In fact, time, place, location, the name of the war, nothing is mentioned in the poem. The poet has done it purposely in order to give the poem a universal appeal, meaning whatever happened to John Brown can happen to any soldier. It can happen to a soldier anywhere in the world, and it can happen to a soldier in any battle or war, irrespective of when, where, why, how they are fought. So, without mentioning any specific name, location, which is the war, the day, the date, the poet has given this poem a universal appeal. Now let us see what is written in the introduction. This poem is a ballad, a form of poem that tells a story with a moral lesson, which I have already told you. The poem follows the traditional form of a ballad with 12 stanzas or verses. Stanzas are also called verses. John Brown is an imaginary fictitious name of a soldier, an example of the many thousands of soldiers who fought and died in wars. John Brown was not a real soldier. It's just a name. If you replace John Brown with the name of any soldier, the story does not change. The poet talks about the pride and happiness of a mother on seeing her son become a soldier. The pride of her son being brave, courageous, patriotic, and fearless. This is what we see in the first part of the poem, where we see through the eyes of the mother. The poet is giving us the conventional idea about people's perception of wars, where they felt that it was a matter of pride if their sons became soldiers. This poem, written in 1962, was in the Vietnam War. It was during the Vietnam War. However, in the second part of the poem, the happiness and pride of the romantic notion of the mother that a battlefield was a glorious place, that soldierhood was a great profession, all these are completely shattered, ruined, when the son returns wounded, having lost an eye, a hand, and his spine damaged. The mother realizes the dark side of a war and a battlefield. You must understand, the mother's romantic notion or idea that a battlefield is a glorious place is shattered, broken, when the son returns home wounded, injured, maimed, and even angry with the mother for being proud that her son was a soldier. Now we move on to the poem. And remember, since it was a song, the wordings, the language of this song or poem is very, very easy. John Brown went off to war to fight on a foreign shore. So John Brown was going to fight a war in a foreign country. See, which war, which foreign country is he going to is not mentioned. That is why it gives a universal appeal to the poem, because it could be any war, anywhere in the world. The result would be the same. His mama sure was proud of him. He stood straight and tall in his uniform and all. You know, the mother, the mama, was very proud of the son. The son looked smart, suave, brave, elegant, wearing the uniform of a soldier and carrying the gun. His mama's face broke out all in a grin. When the mother looked at the son wearing the uniform, the mother's face broke into a grin, a proud smile that her son has become a soldier. This is the traditional view. Parents feeling proud that the son has become a soldier. The figure of speech used in the first stanza, only one figure of speech, alliteration. See, fight on a foreign shore, repetition of the F sound, alliteration. Stood straight, repetition of the S sound, therefore alliteration. O son, you look so fine. I am glad you are a son of mine. You will notice that from the second stanza, the first person conversation begins. The mother talking to the son. The poem has got plenty of dialogues in the first person. The mother is speaking, later the son will also speak. So, the mother said, you look so fine, smart, brilliant, elegant, like a hero in the uniform and carrying the gun. You make me proud to know you hold a gun. As a mother, I feel proud that you are holding and carrying a gun as a soldier. Do what the captain says. Lots of medals you will get. In the battlefield, follow the instructions of the captain, obviously the superior officer. And because of your heroism and courage, you will be winning many medals. And we will put them on the wall when you come home. When you come back home with the medals, we will display the medals on the walls of our house for others to see and admire. You will notice that something bad could happen to the son, that he could be dead in the battlefield, that he could be wounded or injured in the battlefield. Those thoughts never come to the mind of the mother. The mother is thinking that a battlefield is like an Olympic Games stadium where the son is going to win medals. As that old train pulled out, John's ma began to shout, telling everyone in the neighborhood, "That's my son that is about to go. He is a soldier now, you know." Imagine the mother had gone to see off the son at the railway station. As the train carrying the soldiers were pulling out of the station, the mother was shouting and telling everybody proudly that her son was a soldier and going to fight a war. Obviously, she wanted everybody to know that her son was in this noble, great profession by becoming a soldier. She made well sure her neighbors understood. Understood here means heard and understood her pride and happiness. Meaning, she made sure that the neighbors understood that her son had become a soldier. They knew that her son had become a soldier. They also understood how proud and happy the mother was that her son had become a soldier. She got a letter once in a while, and her face broke into a smile. From the battlefield, the son used to write a letter occasionally to the mother, and whenever the mother used to receive a letter, her face used to break into a broad, proud smile. As she showed them to the people from next door, and she bragged about her son with his uniform and gun, she would go to the houses of the neighbors showing that letter, and she would be bragging and boasting about her son being a soldier, how smart he looked wearing the uniform and carrying the gun. And these young things you called a good old-fashioned war? Oh, good old-fashioned war? Now you see something. Repetition. Old-fashioned war! Exclamation mark. This has been repeated. This phrase has been repeated. When I began the poem, I told you that this poem is making an effort to break our traditional, conventional views about wars. That is why the poet is very sarcastically saying here, you all believed that war was glorious, a battlefield was a glorious place, it was a place of showing your heroism, bravery, courage. Nobody ever thought the countless numbers of young men who die in the battlefield. The conventional view was to glorify wars. The romantic notion about wars, that it is something great. That is why the exclamation mark. The poet is sarcastically saying that this was the old-fashioned, conventional, traditional view about wars, where parents felt proud that their sons had become soldiers. They painted rosy pictures of the battlefield. They imagined and dreamt of the sons displaying their heroism, bravery, and courage, and coming back home as heroes, without ever thinking about the darker side of wars, that wars could kill their sons also. Then the letters ceased to come. For a long time they did not come. They ceased to come for about 10 months or more. Finally, the letters from the sun stopped coming. Ceased meaning stopped. For a long time, no letters came from the sun. And after a gap of more than 10 months, finally a letter arrived. Not from the sun, but from a third person. Then a letter finally came saying, "Go down and meet the train. Your son is coming home for." A very cryptic, short, brief letter came to the mother that your son is returning from the war. Go to the railway station to receive your son. Obviously, the letter must have been written by the army headquarters to inform the mother that the son was coming back home. You will notice one thing. Look at the stupidity, the foolishness of the mother. The mother never thought, why did the letter come from a third party and not from the son? Still, she could not imagine that something might have happened to the son. And you will notice the insensitivity of the concerned authority also who has sent the letter to the mother. The insensitivity is because in the letter nothing was mentioned as to what had happened to the son and why was the son coming back. So here you will see two things. The mother not understanding or realizing the significance of the letter coming from a third party, and the poet is also pointing out at the indifference, the insensitivity of the army authorities who are sending a letter to the mother without even informing the condition of the son in which he is coming back. She smiled and went right down. She looked everywhere around, but she could not see her soldier son in sight. Imagine, she smiled when she got the letter. I told you, it never occurred to her, why didn't the son write the letter? She went to the railway station. Standing on the platform, she looked here and there, but she could not see her soldier son. In the line, could not see her soldier son in sight. You will see repetition of the S sound, therefore alliteration. But as all the people passed, she saw her son at last. When she did, she could hardly believe her eyes. You will notice, when the platform probably became relatively empty, she saw the son walking very, very awkwardly and uncomfortably towards her. There was slowness in the way he was walking. But most importantly, his body was heavily bandaged. And therefore, when the mother saw the son in such a condition, her first reaction was she could hardly believe her eyes. Meaning, she could not accept the fact that her son's condition could be like this. She got the shock of her life, and here we see the change in the mood and the tone of the poem. From the pride and the joy and the happiness that the mother felt when the son became a soldier and had gone to fight a war, now she slowly realizes the harsh but brutal reality of wars. On his face was all shot up, and his hand was all blown off. Look at the miserable condition that the son was in and how he had returned home. Half of the face had been blown away along with an eye. One hand had been blown away, and he wore a metal brace round his waist. Probably his spinal cord was injured. He could not stand properly. So, a very broad metal belt was tightly wounded around his waist to make him stand straight. He whispered kind of slow in a voice she did not know. When the son attempted to speak, the voice was reduced to a whisper. It was slow, and most importantly, it was a voice that the mother could not recognize because this was not the way the son used to speak. While she couldn't even recognize his face, O Lord, not even recognize his face. Again, see the repetition. Not even recognize his face. You know, the face was so heavily mutilated, maimed, wounded, injured, half had been blown away, so heavily bandaged that the mother could not even recognize the face of her son. Why the repetition? First of all, the tragedy that a mother is unable to recognize her son, and that is because of the effect of a war. Another thing, why was the shock in the mother? Not only at the miserable appearance of the son, but it is also because what she had imagined and what had happened did not match. What had she thought about? Look at the contrast. That the son would come back with medals, the son would be awarded for his bravery and courage, while he has returned maimed, wounded, injured, mutilated. Her imagination and the reality, they don't match. It was the shock of her life. Oh, tell me, my darling son, pray tell me what they done. How is it you came to be this way? So the mother is saying, oh, tell me, my darling son, I request you, I pray you, tell me, what have the enemies done to you? How is it that you are in such a miserable condition? He tried his best to talk, but his mouth could hardly move, and the mother had to turn her face away. Obviously, the son tried to give an answer to the questions asked by the mother. Because of the heavy bandage and the injury, he could hardly move his mouth to speak out. The mother was no longer able to bear the pain and the suffering of the son, and she turned her eyes away from the son. Imagine a mother turning her face away from the son, a mother unable to bear the misery, the pain, and the suffering of a son, and all because of that war. Don't you remember, Ma? Now, the son is speaking. Don't you remember, Ma, when I went off to war, you thought it was the best thing I could do? You know, the tone in which the son is talking to the mother now, it is a tone of anger, irritation, sarcastic tone. He is saying, do you remember, mother? When I went off to fight the war, when I went to the battlefield, do you remember? You felt very happy. You felt very joyful. You felt very proud. You expected me to come back with medals. You never thought of what has happened to me. You never imagined that I could return home like this, reduced to a mere moving vegetable, having lost body parts, not even being able to speak properly. These thoughts never came to your mind because you were already painting rosy pictures of the battlefield, thinking what a glorious place it was, as if It was a sports ground where I was going to contest and win medals. I was on the battleground. You were home acting proud. You wasn't there standing in my shoes. I went to the battlefield. You sat at home feeling proud that your son has become a soldier. You never had gone to the battlefield. You had never seen the harsh, brutal realities of a battlefield. You were never in my shoes. You were never in my place in the battlefield to feel, to understand, to see what actually happens in the battlefield. What a brutal, miserable place a battlefield is. It's not of courage and bravery. It is not about medals and glory. It is about risk, death, destruction, disappointments, injuries, wounds. These thoughts never came to your mind. Oh, and I thought when I was there, God, what am I doing here? I am trying to kill somebody or die trying. He is saying, when I went to the battlefield, I was questioning myself, what the hell am I doing here? Am I doing only two things? Either I am trying to kill my enemy, or in the process of trying to kill the enemy, I am myself going to get killed. That means either I will kill or I will get killed. These are the only two things I was doing in the battlefield. But the thing that scared me most was when my enemy came close and I saw that his face looked just like mine. Oh Lord, just like mine. Again, see, there is a repetition, just like mine. But the greatest shock that I got in the battlefield was when the enemy came closer to me, I saw that the enemy was not a demon. The enemy was not a devil. The enemy was not a monster or an alien from another planet. The enemy soldier was an ordinary human being like me only. There was no difference between me and that enemy soldier. The point is, here, Dylan probably is referring to the Christian concept of universal brotherhood. We are supposed to live as brothers and sisters. We are fellow human beings. We are there to share, care, love each other. And instead, we are at each other's throats. And what are we doing? We are killing each other. We are killing fellow human beings. Somebody like me. Or he is killing me. I am like him only. That is the true reality of a war and nothing else. That is why the repetition, the tragedy of a war is, instead of living as brothers and sisters, we are killing each other. And I couldn't help but think, through the thunder rolling and stink, that I was a puppet in a play. Now comes, the biting words. When I was standing in the battlefield, I was surrounded by the sounds of gunfire and cannon fire. I could smell the gunpowder. I could smell the rotten dead bodies strewn around in the battlefield. Standing amidst them all, I was thinking that what a fool am I. I am nothing but a puppet. I am dancing to the tune of somebody. Who are those somebodies? Leaders, politicians. They are the ones who start wars and battles, and they send the soldiers to the battlefield to be used as cannon fodder. The soldiers have to do what the superior leaders and politicians want them to do. So the leaders and the politicians are the puppeteers, and the soldiers are mere puppets. They have to follow instructions. They have to do whatever they are ordered to do. And that is what they are doing in the battlefield. Fighting, trying to kill, or getting killed. And through the roar and smoke, the string is finally broke, and a cannonball blew my eyes away. When you go to see a puppet show, you will see the puppeteer uses his fingers and strings to make the puppets move. Here, the metaphor is the string is the cord of life for John Brown. A cannon was fired, the cannonball snapped or cut that string, meaning he got wounded and injured, and that was the end of his profession and life as a soldier, and now he was back home in a miserable condition. You see how very strongly Bob Dylan is criticizing those who start and create wars. They never themselves go to the battlefield. They send these soldiers, the helpless young men who go thinking that it's very glorious, it is patriotic, it's an honor to fight for your country and die and become a martyr. Whereas the true fact is, we are killing each other. Families are becoming childless. Mother is losing son or sons. That is the reality of a war. And the last stanza, as he turned away to walk, his ma was still in shock. Obviously, the mother was in a shock because what she had imagined and thought and what was in front of her today did not match. Her ideas about wars, her thoughts about wars had crushed to the ground. She was now facing the harsh realities of a war. At seeing the metal brace that helped him stand, but as he turned to go, he called his mother close and he dropped his medals down into her hand. This last act is important. As the son was going away, he turned back, asked the mother to extend her hand, and when the mother extended her hand, he put all the medals that he had won on the palm of his mother and walked away. This depositing the medals on the palm of the mother brings out the anti-war theme. The son is sarcastically indicating, Mother, you wanted the medals. You wanted to display the medals on the walls of your house. These are the medals. Display them. Show them to everybody. But also remember the cost I had to pay for winning these medals. I did not die, but I am dead. I am a living dead body because one eye is gone, one hand is gone, my spinal cord is injured. Then what is left in my life? And all these I have sacrificed to fulfill your false dream of winning medals. That brings out the anti-war theme, the action of the son. Please note that in these last two stanzas, you have a few figures of speech. Puppet, controlled by others. Play is a drama. Now see alliteration. Puppet in a play. Repetition of the P sound. Then see the metaphors. Puppet in a play. Who is the puppet? The soldier. The leaders, the politicians enact a drama. They start the war. The soldiers are puppets fighting the war according to the instructions given by the leader. This string is finally broke. I told you, the puppet is moved on the stage with the help of strings. Here the string is the life cord of the soldier, which is snapped or cut, and the soldier either dies or returns home like John Brown, wounded, maimed, and injured. And the last thing, the theme or the central idea. Through the injury of John Brown and through the realization of the mother, the poet brings out the anti-war theme. Though he doesn't say a word against it in the poem directly, He doesn't say wars are bad, do not fight wars, let there be peace. No. Through examples of the mother's contrasting reactions in the beginning and in the end, through the experience gathered by the son actually in the battlefield, through the miserable injury and wound of the son, the poet brings out the anti-war theme. Many people romanticize wars. They think wars and battlefields are glorious and that soldierhood is the best profession. Through the character of the mother, the poet brings out the falsehood in this belief. The mother realizes there is nothing glorious about wars. It's all wrong ideas and beliefs. Her pride, happiness, dreams of medals all fallen to pieces when her son returned badly wounded and disfigured. The mother is now distraught, disillusioned, devastated, dejected, and that is how the poet shows that war wasn't a heroic act, but it is a deception where political masters put the lives of young men at risk by sending them to the battlefield. This is that puppet metaphor. You know, the mother's dream of winning medals is replaced by what? Is distraught, sad, sorrowful, disappointed, disillusioned, devastated, broken, dejected, sad, sorrowful. And that is how the poet is showing that war wasn't something heroic, but it was cheating the young people. Political leaders send these young people to fight wars. They die, their lives are wasted in the battlefield, and that is the reality or the truth of a battle or a war, not the joy or the pride or the happiness of a mother or a father in seeing the son become a soldier and win medals. Thank you.